Hey there, everybody. We're going to look at in the next couple of videos or next few videos some work specifically around the Euler phi or totient function and reduced residues. So the first example we're going to look at is just to compute the powers of 3, the phi of 3 to the m for m equals 1, 2, 3, 4. And we're going to do this directly from the definition. Just so we can kind of get a sense of some patterns of what's going on with this particular function. So we're going to start with just powers of a prime because that's pretty straightforward, and this will help us eventually get to composite numbers down the road. And we won't have videos on all of that, but it'll help you set you up for the work that's in the chapter. So let's start with the simplest case. The first one is the phi of 3. So what is phi? So phi is essentially the number of elements in Z3 that are relatively prime to 3. So 0 is never going to be in here. 0 is not prime to or relatively prime to anything, because basically anything can, or 0 is divisible by anything. So 0 is out of the picture already. Okay. So what's the first number that's relatively prime to 3 in mod 3? Well, 1 is. And the next number is 2. And then we get to 3. Well, 3 is just 0 in mod 3, so we're done. There's only 3 elements in mod 3, and we've already thrown one of them out. So it turns out that we have the elements 1 and 2, and so phi of 3 to the first is just 2. But I'm going to write it down as 3 minus 1 for the moment. That comes in handy later on to think of it. Okay, so that's essentially what the phi function is canceling. Okay, I'm sorry, it's counting. Not certain why I said that. One way to describe it is you could say that it is actually counting how many congruence classes are relatively prime to the mod. So in Z3, if you think about it, we don't have to check 4 because that's essentially mod 1, or that's 1 mod 3. So 4 is part of the congruence class of 1, so 4 would be considered relatively prime to 3. We don't have to count 8 because 8 is congruent to 2 mod 3. So again, 8 is part of the congruence class of 2. Okay, so what about if we go to phi of 3 squared? So just to be clear, this is really the same thing as phi of 9. Okay, so again, we want the number of elements that are relatively prime to 9. Obviously 1 is and 2 is. 3 is not. 9 is divisible by 3, so that doesn't work. But 4 works, 5 works, 6 isn't, but 7 is and is 8. And then we get to 9 and we start over again. So we stop there. So looks like we have 6 elements there, so I can write that. The phi of 9 is going to be 6, which I can also write as 9 minus 3, which, again, like I said, is building towards what we're going for. Let's step it up to q of 3 to the third. So now we're talking about q of 27. And I'm not going to write all these out. We're probably going to start to think about a pattern here. Clearly we have 1 and then 2, but not 3. It's divisible by 3. 4, 5, not 6, because 27 is not divisible by 6, but it does have a greatest common divisor other than 1. So we can throw out basically anything that is a multiple of 3. So 7, 8, no 9, 10, 11, no 12, 13, 14, and so on. So let's think about this, because obviously the larger the numbers get, we don't want to have to list these out all the time. Well, how many elements are in the set of Z27? We know there's 27 elements in there. So if we think about it from that perspective, we've got 27 elements. How many of them are divisible by 3? Well, as we saw from the pattern, every third number is a multiple of 3. 0, 3, 6, 9, 12, 15, 18, and so on. So it turns out that really what we've got is we're taking away a third of the numbers, so 27 minus 3. I'm sorry, 27 divided by 3, which is just 27 minus 9. So there's 18 numbers for Q27. Okay. So the only way the phi function goes wrong is when we're finding these multiples of 3. So we just have to figure out a way to take those out. So if I go one more, Q phi of 3 to the 4th, if our pattern were to hold, so we're looking at Q of 81, then this should be 81, not 18, minus, and then it's the same thing, because all of the multiples of 3 are share a divisor with 81, and nothing else does. So again, 81 divided by 3 equals 81 minus 27 equals 54. Okay? So we don't really have to go any further than this, but let's generalize this because that's going to be helpful. So if we generalize this statement for the Totient function, then we're going to say that Q of 3 to the m is 3 to the m, so it's the total amount of elements that are in that set, minus 1/3 of them. But obviously I can rewrite that second one as 3 to the m and 3 to the m minus 1. And actually that's a good way to think about it. But you could go one more step, and this is helpful later on to think about, and write it as 3 minus 1 times 3 to the m minus 1. In other words, I can factor a 3 to the m minus 1 out. And this comes when they generalize the statement for the Totient function. This particular expression shows up. So it's helpful to kind of think of this. And this works for any power of any prime, where we just replace the 3 with whatever prime we happen to be looking at. Okay, and that's just basically using the definition. We'll look at some other examples next.